The model uses all available data on customers and account level, inclusive of behavioral data and operational data, CRM, operations, usage, interactions, complaints, tickets, billing and financial records, customer experience feedback data in terms of NPS, customer satisfaction or equivalent, dedicated survey research data, which could be transactional or relationship, historical records of interaction and feedback. The entire modeling goes through 5 distinct stages that are interconnected and interdependent. Data environment design. This is the most creative part of the whole process. Here we make a thorough data audit and data description. We define data exclusion rules, look closely at potential classes that we want to predict. We also make an extensive data mapping, which all goes into master data file design, develop model validation technique, and design the model performance blueprint. Data preparation. During that phase, we start by combining all data sources and all variables, a tedious process that considers all variable specifics on the lowest granularity level that allows aggregation. Closely followed is the variable recording. We transform categorical values into dummies and apply additional aggregation on numeric ones. A common practice we apply also includes variable imputation, that is replacing the missing values, using a separate model or other simpler data augmentation techniques. As a result, we end up with a huge data file, sometimes accounting for more than 3,000 variables, which is ready for the next stage. Descriptive analysis. During that stage, we apply all standard statistical methods that generally summarize the distribution of the raw data. By applying correlation and vintage reports, as well as all known types of statistical testing, we look for similar variables which could be eliminated if closely related to others. We prefer Bayesian methods such as factoring for more robust results. Apart from that, we look at how good all variables explain the variance in the target variable and the classes. Those with higher than usual impact are being penalized so that we get a sort of diversity when it comes to variable predicting the NPS. We do not want to put all our eggs in one basket. At this stage, we also look into different groups and subsamples of the population. If there is a significant indication of increase in model performance for different segments over a single major model, the entire modeling stage is split into separate population for which separate modeling processes take place. Predictive modeling. Next, we start by application of standard data science approach. We split the data into training and testing. Based on the model validation plan we've created in the first stage, we determine which models to use and how to define and tune the specific hyperparameters. We usually start with a simple linear model so that we could have a starting point. It is a benchmark used to get our bearings with the other models we develop. The linear model is the one we like to refer to as a saturated model. Then, we apply penalizers based on variable importance and predictability. Further, we apply nonlinear models. We start with bagging and boosting methods, random forest, LGBM, and etc. And normally end with neural nets of different type, most commonly feed-forward fully connected with L1 regularization or LSTM. All of these are individually trained and verified, and their performance benchmark against the saturated models. The one that proves the best wins the race, and it's used for main prediction. Model evaluation. The target variable is a binary outcome derived from the NPS, where definition of super detractor is NPS values between 0 and 4, but definition varies. On the right hand of the equation, are those variables that prove to have the highest impact on the NPS. The model performance is evaluated by the area under the curve or Gini coefficients. We also tend to look at the precision and recall. We refrain from using the accuracy since in most cases we deal with very low percentages of cases we need to predict. The preferred model would ideally perform the best, has lower complexity in terms of implementation, and would be easily adjusted for scalability. A final model performance aspect that is worth mentioning is the variable importance. The approach for calculating includes two methods: analyzing different sets of variables via combinations of linear models, or using Shapley additive explanation, also known as SHAP. These are model agnostic, which means that they could be used for different modeling techniques. The reason behind the two-method approach is the ability to compare importance with another type of model, for example, random forest, GBM, and so on, with less bias and hopefully with better performance. Empirical probability calibration. When performing classification, it is often desired not only to predict the class labels, but also to obtain a probability of the respective label. After the modeling is completed, the predictive values represent only a rank that could only be compared between predictions coming from the same model. Thus, they are not probability, nor they can be compared to values coming from other models, or compared to any of that metric for that matter. The predicted values are simply ranks that tell you that one order has higher probability of having been made by super detractors than other. What is behind the actual probability cannot be stated without an extra step of the calibration. The well-calibrated empirical probability gives you a high level of confidence in the prediction and its meaning. Some models can give you poor estimates of the class probabilities, and some even do not support probability prediction. In other words, the calibration represents a model with one independent variable, the produced score, from the selected model, while the dependent variable is the actual observed event rate model or some other close related event that in this case could be the NPS estimation. Now, let's look under the hood. The whole technology stack gravitates around three main modules. Backend module, the actual data modeling procedure that we just talked about. API module, which connects and implements different algorithms for individual services implemented and exposed to the end users as endpoints. And finally, the database module, which holds the entire data stack, not only the raw data coming from the uploaded dataset, but also the outputs of different stages described previously. All the three modules communicate seamlessly among each other, which makes the whole production line going smoothly and in parallel. It all starts from the development environment, where a team of data engineers and data scientists are working on developing the entire code stack for the application, considering specific data and requirements which vary from client to client and from project to project. This initial phase is particularly important and takes a lot of creativity and planning to ensure the seamless execution of the next stages. Once ready, all code and setting files are pushed through Git protocol to dedicated Bitbucket repos, which hold only the latest version of the uploaded files such as Docker files, Kubernetes config files, etc. Thus, we ensure that the subsequent process uses the latest version of the files without the need of adjusting the actual API manually. On the other hand, it also enables different changes in code to be consumed without the need of redefining the whole stack if sudden changes occur during the actual execution. From there, all callbacks are attached into the pipelines through a useful tool called webhooks. The CI/CD process are completely automated. The second synchronization palette, which is securely connected with dev environment, is the Docker Hub. There are a series of containers and container settings and images stored so that every time the actual API is triggered, a new container, that is a virtual machine, is built with the same shape and size. In fact, the Docker Hub contains instructions and has a similar purpose to the Bitbucket, with the only difference that it contains images or snapshots rather than code. In general, when not in use, the production shuts down all containers so that no resources are to be spent in vain. The only available resource, which is active at all times, is the one holding the database, so that no data or progress is lost under any circumstances. The database is built on Postgres and serves three main purposes. It stores the raw data provided by the client as an ultimate source of truth, the model performance diagnostics, scoreboards, results, and final scores, which is the ultimate output we all are expecting from the model. The database has multiple endpoints which establish connections to external sources such as clients' databases or internal APIs for data manipulations and modeling. It could also be connected to a dedicated visualization tool which consumes the data outputs. It also resides in a separate container managed by the Kubernetes cluster. To connect the three different modules, we use a series of deployment pipelines and predefined commands, all aligned in Jenkins automated server, which also resides on a separate Docker container. The Jenkins server contains dedicated instructions for every pipeline, stage of the cluster deployment process, and it serves like a switchboard. Every action needed is recorded as a set of instructions in the pipeline that are triggered in a predefined sequence or upon termination of adjacent processes. For example, you start the API service deployment upon finishing the cluster deployment process. Jenkins also provides ways to optimize the entire process and cut down costs and time by turning on the required modules and switching off the different instances when not in use. The entire process starts by building a service cluster in the cloud. We decided to use AWS, but the entire process could be easily implemented within any cloud-based environment, even internal client's domain. For setting the environment, we need AWS cloud resources and deploying K8s clusters with KeyOps Kubernetes operation using a shared VPC, Internet Gateway attached to the VPC, and an S3 bucket for volume storage. The cluster is managed by KOPS, which builds the necessary number and types of machines by taking the instructions from Jenkins and runs the pNPS services on the cluster machines using the respective Docker images from the Docker Hub and source code from the Bitbucket repos. The number of nodes in the cluster depends on how many active projects run at a certain period of time, plus one master node, which contains all processes and calculations relevant for all. The system also allows different nodes to be located in different cloud services and geographic areas based on client security protocols and requirements. The master node contains API server, scheduler, and control management system for resource optimization. The other nodes contain separated databases with specific data, modeling instructions, and individual settings. Thus, one engine could be used for different modeling purposes, different clients, even different prediction tasks if all of them follow the same principles as the others. The entire process is over once all variables are processed, data is consumed, and the database is populated with the most recent and most accurate predictions for the entire customer base. A separate optional module represents the process output, model performance, variable importance, and overall modeling diagnostics through series of visuals and logs which are easily downloadable and accessible by product consumers. Additionally, we provide accuracy report and summary of findings on aggregate and customer segment levels.